Well, good morning or afternoon, wherever you are, in whatever time zone. It's 5:30 in the morning here in Phoenix, Arizona, and we're having almost perfect weather this time of the year. It's getting a little cooler earlier this year than normally, but I think we still have some hot days coming. And so thermal is not only a hot issue out in Phoenix here during the summer, but it's a hot issue with our team of developers that have been working for, well, some of us since the 80s on developing thermal tools. The topic today is looking at some of the challenges in spacecraft thermal design. There's some things that are a little difficult to do and traditionally consuming, and we've tried to add features to our software to help alleviate some of these time-wasting features and make things a little bit easier to do and make your thermal design more productive. Let you focus more on the design and not so much on the software. So let's go through a few slides first, and then I'll show you some live demos of the software itself. So one of the things you want to do is try to quickly understand a thermal system. Frequently, you want to use CAD tools to create your thermal model. Modeling thermal radiation is critical for spacecraft thermal design, since that's how you get rid of your heat, and you get some heat gains also from solar loads. So having some a variety of radiation features, thermal radiation modeling features, is important. Modeling joints and interfaces is critical in thermal design of spacecraft. You may have a bolted joint that works very well on Earth, but when you get up into the vacuum of space, things can just, those connections can just disappear when you get a vacuum. Even though it's a good structural joint, it may not be a good thermal joint. I've seen some big changes on electronic equipment and boxes that may work at room temperature, but then certain devices will fail because they no longer have convection, for example. MLI and heaters and some thermal features such as those are not always easy to add in software, so we've tried to make that easy, and I'll show you examples of that later. Modeling complex kinematic motion. A lot of spacecraft have doors that open and close and solar panels that unfold and articulate, and we have some very powerful kinematic modeling features. And then assembling these into a complex mission where you may go through several different geometry and pointing states. You may have things deployed at one state or things open at one state, and then reorient the satellite for a charging state and close the door or something. And I'll show you some complex missions that combine complex motion with a series of sequences of events. And then sometimes we need to model solar loads on the Earth, such as a satellite on a rocket and a shroud baking in the sun. Before I get into showing you the graphical modeler, I want to say something about the solver that we use, Sinda, which is 50 years old now. Sinda came out in the Apollo program back in the 60s, and it's more than just a thermal solver. It's really a thermal programming language. A lot of people understand how to use it because it's intuitive, using an RC resistor capacitor sort of concept of thermal masses of nodes and thermal resistors modeling conduction, convection, radiation. And the models we create from a modeler like Patran or Thermica, we turn into these resistor capacitance, this RC model. But you have we have a GUI in Windows we call Thermal Studio, where you can open your models. You can have multiple models, make copy of it. You can run and get different result sets and do plots. You can update your model and change things, and your plots will update. So we have a way of you just dealing directly with the model, and you can launch your model right out of Patran. So if you want to work at the Sinda level or just want to do multiple cases and do some small changes to the model, you can do that all in Thermal Studio, a Windows GUI that comes with Sinda. Users can learn to add programming logic or equations if you need to add something. Maybe something simple like if time's greater than 1 hour, then do this. Turn off this power, turn on a power or something. It may just be one simple equation, or it may be a whole subroutine. And Sinda, because it's intuitive, people can figure out how to use this. It fits heat transfer books that talk about thermal resistors, and people can figure out how to use it in looking at some of our training material and start using it only after about an hour of training. And as I said, it has a full Windows GUI. And then Sinda, of course, transparently integrates into our modeler, Patran, where you can do 3D modeling using CAD geometry. So when we plug into Patran, we still have the full power of Sinda. We have also Thermica or Sinda-Rad, two different technology radiation codes. I'll be demonstrating those in a model. We can even mix both of these, use Sinda-Rad on the inside where you may have 10, 20 million, or 100 million view factors. Use Thermica on the outside where you have orbital heating, specular, bouncing around, because Thermica uses a ray tracing technology where Sinda-Rad is a high-speed hemicube solver, and so it works better on internal cavities where you have lots of view factors, and Thermica would work better where you need the orbital heating on the outside typically of a spacecraft. So we have two different technology radiation solvers that can be mixed and matched even within one model. And even though we plug Sinda into this nice graphical environment, you still have the ability to add equations and programming logic through the Patran GUI. You can call that up and create skeleton files that automatically will get added to your thermal models. When we talk about spacecraft thermal design, there are several things that we can use to control the environment of our spacecraft. You have things like batteries and electronic equipment that are temperature sensitive. Batteries, typically you don't want to get down below 5 degrees C or something, and electronic equipment may go colder than that, but you can get it so cold that you can damage electronics or batteries very easily. So we put heaters sometimes on spacecraft when the sun's not shining or when it's in an eclipse, and we use thermostats to turn heaters on and off, either proportional or bimetallic on-off. We use multi-layer insulation to protect parts of the vehicle. We use radiator panels to get rid of heat. We can change the orientation of the spacecraft in orbit. We might add louvers or something that is a variable, affects the radiation based on the position of the louver. Might be heat pipes, either constant or VCHP, variable conductance heat pipes. And then you might control the conductance between a component and a radiator panel by putting thermal grease to make sure it's well tied into a radiator panel, or you may want to purposely break the conduction between a component and keep it isolated from some hot or cold part of the spacecraft, so we can use conduction. And by relocating components, that's another thing you can do. So in our tool here, we've tried to make all of these items here on this list that thermal engineers need to play with as they're working out a good spacecraft thermal design. We've tried to make these things fairly easy to model. Let's talk a little bit about contacts, because this is very important when you get into the vacuum of space. We have three types of contacts. We have edge to edge, like you see between these two plates here. We have edge to surface, which you see between the edge of this plate and the surface. And then we have surface to surface, which you can see the bottom of this cylinder going to this plate. And if you can see these small little lines here, these little bar conductors, these are automatically added by our software. All you specify, you want that edge hooked to that edge, or that surface projected down onto that surface, and it will look at your meshes and hook up the right conduction for you. And we do that in a fairly sophisticated fashion and do it as accurately mathematically as possible, even though the meshes may not line up. We also can model, use this feature to model convection in a tube if you have any liquid cooling on a spacecraft, or even external flow over things. And we have about 40 different correlations that you can use because sometimes convection through liquid cooling or something is used on spacecraft, or on the ground, air blowing through a spacecraft. And these Sinda conductors at these contacts are added actually at runtime. So if you decide to remesh something and rerun it, it will hook up the new mesh at runtime. And then we have a way to visualize it, as you can see in this picture, and I'll show you that in a little bit too. Here's an example of putting, it could be a chip on a board, or it could be a transmitter on the wall of a satellite, a radiator panel, and it's projected on. And here there's no gap. Sometimes we leave little gaps just so we can see, but whether there's a gap or not, we project one surface, this bottom of this box, onto this big surface, and then we hook up the nodes. So it's actually done at a geometry level. You can do it at an element face level or element edge level, but typically we do it at the geometry level. You can do this even without a mesh, or turn off the mesh and just deal with the geometry, and then whatever mesh you use, it will then hook up the right elements. So that's done fairly easily, and I'll show you that in a few minutes. When it comes to radiation, we have several different options. There's obviously simple things like free radiation off of this plate, where I could just specify a view factor and an emissivity. But when you get into spacecraft thermal design, you have a lot of surface-to-surface radiation, so we want to compute these view factors. And so we have different methods for doing that. And we have three methods, or three different philosophies kind of with our radiation code, Thermica, which is a ray tracing code. We can either do small faces, where we take every little one of these elements and make it like a flat plate and do radiation from element to element. We can do something called super element, where we'll group all these small little elements, or all these elements on this hemisphere, into one radiation super element, and then in that case we'd only have one view factor between these two surfaces. To take maybe CAD geometry that you mesh kind of finely from a conduction standpoint, we can then group some of these elements together and make larger radiation elements if we want. Or we can actually use true geometric primitives. We support several of those, like hemispheres and parabuloids and spheres, discs, cylinders, all in Patran, and those get sent to the radiation code as true geometric shapes. And you can see down here we ran this with three different methods, and you can see the runtime with the primitive method or the super element method that combined some of these into one, ran much faster, but yet we still got basically the same results. I want to show you an example of multiple radiation enclosures, because this is especially useful for spacecraft. In this case, we had an electronic box here, and we had some PC boards in here. They had contacts to the edge. There's a lid on this box, and it was an enclosure in here. And so we called inside this box enclosure number 1. We had a cylindrical disc here. It could be like a reaction wheel, and we actually had radiation inside that. And that was enclosure 2. Enclosure 3 was actually inside the whole satellite. It had 6 sides and a top and a bottom, plus the outside of this box and the outside of the cylinder and the disc there were all part of this internal enclosure. That was enclosure number 3. Then our 4th enclosure was the outside of the satellite. The surface is pointing outward. And in that case, we used Thermica for that 4th enclosure, and we used Sinda for all these internal enclosures, and did diffuse radiation, where we could have done specular or diffuse on the outside if we had mirror-like surfaces where sun were bouncing off solar panels, the glass on solar panels, for example. And Thermica can handle that. Here's some of the results. You can see the temperatures of the cards here, and this box is mounted to the wall, and this cylinder here is mounted to this wall, and these were 2 radiator panels on the spacecraft. Let me just drop into that model to show you a few things within our software. So here's the model of the body of the spacecraft, and if I look at a group here where I've removed 2 of the walls, you can see inside. And now let's drop in a couple components, like what I'm calling a reaction wheel here, and this electronic box. So there's, let's see. you can see the reaction wheel is on this side here, and there's a little bit of a gap between the reaction wheel and the radiator panel it's tied to, and that's okay because our contacts we call projection contacts. They'll actually take the cylinder, the bottom part, and if I turn off my elements here for a minute, let's erase elements, it'll take that bottom part of the reaction wheel and connect it to that panel. And the way we do that, if I come under my loads here and I look at my contacts, which is a convection type load, and I look at the reaction wheel to the wall, I have a contact coefficient, and then I have you see surface 5 is connected to surface 20. So this surface here, which is surface 20, is connected to this surface 5. So what happens is the small surface 20 is projected onto the larger surface 5, and it will then find all the connections between those two surfaces. So let me turn back on my elements, and let's visualize, go into our groups again, because when we add something like a reaction wheel and connect it, there's a visualizer that gets created automatically for us to show us how that got connected, and it will show you every node that gets connected to the wall and how they're connected. The same with the electronic box. It was attached to the other wall. So you can see how the nodes are hooked up by all those conductors, but you don't actually have to define all those conductors. You just say this one surface is hooked to this other surface, and then we'll hook up all the nodes. If you decide to remesh, then when you run again, we'll hook up the nodes again. Let's look at one more thing here. Let's look at some power. We have some power into the reaction wheel. We have power into the 5 PC boards. And this is just a constant power. It could be time dependent. But we could also, if we wanted to put a heater on this wall to protect it in case you go in an eclipse and the power, you have low power and things get very cold, you can put a heater. We could define that power into that surface, and this is a total sort of heat, so we could say we want to put like 20 watts or 50 watts into that panel, and we could say use an on-off, and we could actually go specify where we want our thermostat to be at what node. We could do a proportional heater, or we can even do a PID controller where you have gain constants that you have to set up. So we have different heater designs that are built into the software. And then finally, when it comes to materials, we have a material library we can open based on Excel. We can maintain it in Excel. You can have coatings and materials. You can create coatings, simple coatings like black paint or white paint. You do advanced coatings that have specular and diffuse components, and also transmission for transparent or translucent surfaces. And then we have something called MLI, where instead of just giving an alpha and an epsilon for a coating, we also give the E star. It's an effective emissivity through the blanket. It's a radiation gap. And when you apply that to a wall like MLI on top of this, it will actually do a double node, and the heat flux goes into the outer node, and it'll have that E star gap. And it'll do that all automatically. And even though when you look at your radiation load, you only have to come in here and look at this MLI load, we just pick the material. We said we're using material, we picked the MLI material that was defined, and we use that instead of specifying an alpha and an epsilon like we might specify on another part here where I've specified an alpha and an epsilon right here. I can actually just come in and say pick a material and pick a material. If I pick a white paint, it's just going to do radiation off that surface, but if I pick MLI, it's going to do that double node on the surface all automatically for me, put the heat flux into the outer node, and have that radiation gap that simulates modeling the MLI using what we call the E-star method. So those are some of the things we've addressed in the software. And now let me close this model here, go back to my slides for a minute, and then I'll show you a couple more demos. Here's just the process of going beginning to end of building a spacecraft model. You might take something like this Hubble telescope, which now the James Webb Space Telescope at Northrop Grumman, they're using Sinda out there to model that. It's one of the biggest models I think ever been created in Sinda. And this is a very simplified model of the Hubble telescope, where I have a disk and a cylinder and a couple plates that might track the sun, solar panels. And so we start by just building or importing the geometry. And if you import it, you can clean it up and mesh the geometry, or recreate new simplified geometry on top of the CAD geometry if you want. You can add materials and then coatings. You add what we call properties, because thin plate elements need to know what their thickness is. Then you can mesh the model. And then once you're ready, your geometry is all prepared, you can go and add radiation loads. You can add contacts between surfaces. If you want to tie the edge of that solar panel to a node here or something, you could do a contact in there, and then add any electrical powers or heaters or thermostat controlled power. And when you do radiation, we have different methods, including this primitive radiation, where that cylinder, we may mesh it 16 around and 12 down or something like that from a conduction standpoint. From a radiation standpoint, we could give it an AB mesh in this direction and this direction. We could make it 1 by 1. We could make it 4 by 4. We could make it 8 by 8. We could do anything we want by specifying an AB mesh on these primitives. So when you're using primitives, whether it's a rectangular primitive like this, or a cylindrical primitive, or a disk, or a paraboloid like an antenna, or a hydrazine tank, maybe a sphere, you can specify a different radiation mesh that's different from your conduction mesh. That allows you to bring in CAD and mesh things finely and have then larger parts, either group elements together with our radiation super element concept, or use primitives, and keep the radiation model simpler than a conduction model, because radiation view factors go up exponentially sometimes with the number of surfaces. So you really want to try to keep the surfaces down to 10, 20,000 surfaces, depending on if you're talking about detailed payloads and internal things or external things. But externally, you surely don't want to have, usually it's in the thousands typically to get good response. Otherwise, you're sitting there waiting for the software for a long time. And then when you hit run, we automatically transfer this to Thermica, and we use Thermica to calculate the orbital heating and the radiation exchange factors. That can be either specular or diffuse, or a combination of both. And so you get your model right in Thermica. We set up the mission, how it's pointed in orbit, if these solar panels are tracking the sun, and maybe this is pointing towards the Earth or something. We set up all of that, and then we can do some post-processing of the radiation and orbital heating results, such as absorbed flux, and we can produce animation and actually produce movies, even HD movies, widescreen movies, in MPEG-4 format. So you can make nice things looking at your results, movies for presentations. And then when you close Thermica, after you've computed your orbital heating parameters and your view factors, we fold all that data back into our Patran model, and we calculate our temperatures based on this Patran model and the conduction here and all the thermal features you've added in Patran, and now you have nodal temperatures, the temperatures at each node in this model, and this could be used for thermal stress and Nastran or thermal distortion calculations, like on a mirror or an optical payload. So I'm going to show you an example. This is actually a workshop. It's a long workshop. I think it's 90 pages. Most of our workshops are around 30 to 60 pages, but this one is really long. And it has you build this whole satellite and then go into some complex mission planning. So let me show you this model. Go back into Patran, and I'll drop into Thermica and show you how the two connect together. So that was our workshop number 9. And here's the spacecraft that you'll build in that workshop. And it takes about a day to do this workshop because there's a lot of steps and it gets into a lot of detail. But after we have a simpler workshop on spacecraft thermal design and a couple others on radiation, but this is kind of the final exam of our workshops as far as spacecraft thermal design, and you'll probably spend about 6 or 8 hours on it. Not so much building the model. It builds pretty quickly with a paraboloid here and some flat plates, and then we actually do radiation within this cavity, and on the outside we use a multiple enclosure concept. So when you go to run and you set up, you can set up a method such as Thermica for the outside, and we can set up Sinda for the inside. So let's go ahead and just run this. And when I run it, the first thing it's going to do is build my radiation models for my 2 enclosures. And it's launching Thermica to do the outer enclosure now. And I want to show you the mission that we have set up here. First of all, it brings in the model with all the materials and the mesh that was in Patran. I've predefined a mission here, which actually has 3 orbit arcs. It changes the elevation of the orbit. And I've set up kinematic, our pointing laws to rotate the solar panels, set times to track the sun. There's actually 3 what we call phases. At one time, I've just have the solar panels rigid, and the whole spacecraft is pointing towards the sun. So we have a sun pointing. Then we have a small roll maneuver where it rolls from the sun pointing to earth pointing, and then it goes into earth pointing where the solar panels are tracking the sun best they can, where the body and the antenna is pointing towards the earth. So we have these 3 phases, and then we can create a mission that uses sequences. And on this first sequence, I'm using sun pointing, then I'm doing my roll, then I'm using earth pointing. I could then continue on this mission and do another sun pointing and another roll and another earth pointing and reuse these phases over and over again, as you'll see in the next example. But when I run this, it first is sun pointing. You can see this site's all lit up because the sun is right there. And so I'll slow this down a little bit, and the animation probably won't come over real well on the webinar, but it's tracking the sun as I move, and I'll slide my scale over till I get to this event right here where we go into this kind of a little yaw pitch roll maneuver that we've defined in our kinematic laws here. We actually created an Excel table of, or no, in this case we didn't use an Excel table. I actually used a roll rate in different axes. And now as I run it here and we get into this maneuver right in here, you'll see it will start doing a yaw pitch roll, and it goes from a sun pointing and it points the antenna towards the earth, and then it gets into this last phase here, which is the phase where the solar panels are tracking the sun. So you can see they're lit up here best they can. They're tracking the sun, but there's only 1 degree of freedom that we have. If we had another angle in there, they could do a better job of tracking the sun. But they're doing the best they can with this orientation and constraints that they have. So that's a more advanced mission and how you can set up different motions. And then we would come into our processing tab here, and we would basically, we're running 3 processes in Thermica. We're calculating the view factors, we're calculating the solar flux and the planetary flux, which also includes the albedo of the solar bouncing off the planet. And I'd hit run, and this takes a couple minutes, actually about 3 minutes I think this model takes, but I already have the results, so I'm just going to quit and not save anything. And it will take those results, fold them into the thermal model, and you may have seen Sinda pop up. That computed the view factors on the inside of the spacecraft. And when we do our thermal setup here with multiple radiation enclosures, it's possible with these enclosures to make them active, to deactivate them, so you turn them off. Or we can also say, like on the inside here, Cinderad, reuse existing results if they exist, or with the Thermica also, the outside of the spacecraft, we can tell it to reuse existing results. So you can just rerun part of the model if you want, and it's very easy to do through this management screen here on assigning what radiation code and what parameters to each enclosure. Now, Sinda is actually running here. It's going through time. It's at 400, 500 seconds out of 7,000 seconds. So I'll just stop the run here. And now I'm going to show you one other model that has a this spacecraft here orbiting the Earth, and it's even doing some more complicated maneuvers. So I'm just going to go into Thermica and show you that. And I'm going to open the mission file here. And this is another workshop that we have to teach you how to do complex missions. So this mission is even more complicated than the other one. It had several different phases. If we look at our kinematic laws here, we have a wait phase where it's kind of a benign thermal state. We point the telescope towards the Earth, which is the warmest thing to do to keep it at a warmer temperature. We have an acquire phase where we acquire something on the ground. We have a charge phase where we point the solar panels towards the sun. And then we have this Toulouse phase where we actually come in and are reading a table, a text table that has rotation about the XYZ axis. It has some arbitrary scanning back and forth. And then we create this mission here, and let's make it a little bigger here. And on this timeline, you can see a bunch of sequences that I've created. And I've created first a wait state, a charge state, my tracking over France. Then I'm going back to the charge. I'm going back to the wait. So these are kinematic phases that I've defined a certain position of the spacecraft, and I'm reusing these different kinematic positions that were defined over and over again to create a realistic mission. So when I move my slider here to the wait state, you can see we're pointing towards the sun. Let's get to another wait state here where we're out. I mean, not pointing to the sun, we're pointing towards the Earth, but it's kind of dark there. We're in a shadow. Let's get all the way to the end here. Here we're in a wait state at the end, and well, when we're in the sun, we're normally charging the panels, so we're actually in a wait state on the eclipse sides. But you can still see the Earth there a little bit of sunlight. And then when we're in a charging state here, now the solar panels are pointing towards the sun over here, and as we animate this, they'll track the sun. And then when we come to this special event called Toulouse here. This is where the spacecraft follows this table and will actually scan back and forth. You can see it a little bit moving back and forth as it's going about this axis here, scanning back and forth, taking pictures of this particular location. So this is an example of a complex mission and how you can create multiple events. We could have solar panels opening and closing, doors opening and closing, lots of power within this kinematic module to define things like that. So let's hit a couple last view graphs and then we'll be done here. There's also interplanetary things. You can fly from one planet to another, and we can actually use within the trajectory, when we define a trajectory, like we want to create a new arc, we can actually pick a time, position, velocity arc, and we can actually use something like Satellite Toolkit, an STK, a .e file, to bring in that time, position, space information. And I have an example of flying out to the moon, and it flies out to the moon and then loops around it a few times on a lunar mission. We can also, within the kinematic module, we can bring in some kinematic motion from Satellite Toolkit. So we can bring in Satellite Toolkit data. We can create our own missions using Keplerian motion sort of things. And we can do missions to other planets. In other planets, we actually model the emissions from the planet. We can put a hot side and a cold side, and temperatures there, like Venus is much hotter on one side than the other side, and you'll get varying flux as you go around the planet. Or we can do detailed albedo maps or planetary flux maps if you need that kind of detail. Or you can even fly to other planets and not just go around a planet. And the final thing I want to mention, sometimes you're sitting a satellite in a shroud, whether it's transportation or sitting on a launch pad in Florida or the equator, and you're baking in the sun. We have a new feature in our 2013 software that we can do actual realistic solar heating on this. We have weather data from over 2,000 airports around the world. It's hourly data. It's averaged over the last many years, and we have hourly data for every day of the year. We have a moving sun that moves across the sky with a direct solar flux. We have something called diffuse solar, which will bounce off the atmosphere. We can create cloudy days to see how a cloudy day will be different than a sunny day, because on a sunny day, the sun might only hit one side of this, but on a cloudy day, you're going to get solar flux into all the sides because of the stronger diffuse term. So you can actually sometimes on a cloudy day get a worst case, at least for some parts of your vehicle. We also have interaction with ground in the launcher you can build. We can do ground models and get deep ground temperatures. We have sky temperature and air temperature. The sky temperature we radiate to, the air temperature we convect to. And we can create something we call design day, create worst case hot, cold cases for a particular location, where we can say search through June through September, and at every hour find the worst normal flux or worst diffuse flux, and at every hour during that 3-month span, and create an artificial day that will encompass the worst we could ever see. And here's an example of an airplane sitting on the ground where we did a design day where we had what we call the max normal, the moving sun was max here, and here this was the max diffuse, and so it actually didn't get as hot. The range was much less, and you can see the shadow on the ground, this concrete runway, because it's being shaded, and there's interaction, radiation, and you can have convection interaction with the ground if you want to add that. So if you do have a spacecraft on a launcher or sitting out in the sun or some environmental loads, we can do that. The software used in this demonstration was Sinda for the thermal analyzer, Patran, which was our model builder with the Sinda plugin, Sinda Red, which is our high-speed hemicube method that runs on multiple processors, multiple cores. Thermica also runs on multiple processors or multiple cores. And then we have all of these top 3 bundled in a package called TFEA. That's just a kind of a thermal FEA package that has Sinda, Patran, Sinda Rad with the optional Thermica for spacecraft thermal design. And we have workshops. We're working on number 16 right now for our new release that comes out in November. And I think there's 14 in our last release, and we'll have at least 3 more in a new release. And these are self-teaching, and you can learn how to do even thermal distortion of like a mirror here, where you take the temperatures you compute with Sinda and Thermica of a mirror, maybe of a telescope in orbit, and then run Nastran and get thermal stress, thermal distortion. We have a workshop showing you how to do that. Even if the Nastran mesh is different than the structure, than the thermal mesh, we can map the temperatures from one mesh to another. So that concludes the presentation, and we're ready for questions.